Thank you. uh, Sorry, I'm a little bit nervous. This is our last session. Let's start. Hello, my name is Hyungkyu Min, and I'm a researcher of the Korea Quantum Computing. Today, as a researcher of the K.Q.C, I'm going to introduce our research project. Most of our research team members are majoring in the data science and statistics. Therefore, the K.Q.C research team have focused on applying the quantum algorithm into data science problems. One of our main problems is variable selection. Today, we're going to see our research project about quantum variable selection. First of all, we're going to see our target problems. Our target problem is variable selection, especially of the linear models. The linear model is rhetoric model analyzing the linear relation between input and output. For instance, we can analyze the reaction between weight and height using the linear model. The term linear can be understood as linear combination of the linear algebra. The linear model builds the model using linear combination of design matrix like y equals beta 0 plus x1 beta 1 plus x2 beta 2. It is safe to say that the linear model is most important model in the data science. First of all, the linear model is important because almost every statistical analysis and data science models are based on the linear model. Therefore, by studying the properties of the linear model, we can develop the result into other models. Secondly, the linear model is a parametric model that can give us a powerful statistical inferences. For instance, it can give statistical test about significance of height on the weight. A lot of fields such as biology, commerce, and social science use the linear model as a framework of statistical inference. For this importance, we choose the linear model as our target problem. However, there is a big obstacle in building linear model. If the number of features is too many, it will increase the standard error of the estimator of the relation. If it is, the model's statistical inference and predictive power are really hampered. So we have to shrink the number of features by selecting them. The variable selection is literally the problem about selecting the variable used at the model. The variables can be seen as features, factors, or prior information to predict some target variables. For instance, let us assume there is a data about patients of internal medicine. We have information about patients' height, diet, age, and etc. If you want to figure out what and how some factors impact on the lung cancer, we can use the information to see. However, if you use too many numbers of the factor, the model cannot capture the exact reality. For instance, because the region and nationality are similar with each other, they might be insignificant in the model when using both of them, although they are significant when using only one of them. Therefore, we have to select the factors to see exact effects. The problem is, it is hard to find the optimal combination of the factors because the information of each variable is correlated with each other. Therefore, to see the best combination of the features, we have to explore every combination of the features. If you have p numbers of the features, the number of the combination becomes p to the power of 2. For instance, if you have 10 number of the features, then the number of the all cases becomes 124. If you have 100 of features, it's almost 30 to the power of 10. To have the understanding, the total number of bacterial cells on Earth is estimated as 5 times 30 to the power of 10. Now, let's see how can we solve the problem. The conventional statistical approach is Russell regression. The Russell regression using L1 penalty to find the coefficients. By restricting the beta, the algorithm tends to set the coefficients of uninformative feature as 0. Therefore, the uninformative features are naturally be eliminated. The Russell is really powerful and fast, but its estimator is biased. Therefore, to use the Russell coefficient, there need additional statistical inferences. Compared to A, the genetic algorithm is approached based on the optimization theory. It is used at the optimization problem with a lot of local minima and intractable structure. The genetic algorithm is an algorithm imitating the evolution process in nature. It finds best solution by evolving generation of candidates through selection, reproduction, and mutation. It is powerful and flexible algorithm, but it is super heuristic algorithm, which have too many parameters to handle. The simulated annealing is also an approach based on the optimization theory. The simulated annealing is algorithm imitating the annealing process. By repeatedly going up and going down the hill, it can avoid local minima and find global minima. It is also efficient and powerful algorithm. However, the solution of it is inconsistent, and like genetic algorithm, there are too many hyperparameters to handle. On the other hand, there is a quantum approach to solve the combinatorial algorithm. Based on the theoretical and experimental study, the quantum approach is expected to show better performance at the combinatorial problem than classical algorithms. It shows relatively good performance even when the scale of the problem becomes bigger. The base work of our project is quantum feature selection, published at the 2022. The paper suggests algorithm aiming to optimize the following objective function. The objective function contains 3 components. The first one is redundancy term, which is embedded as Q. The redundancy could be understood as degree of information overlap. The algorithm eliminates the redundancy among the features. It can be understood through max-cut problem, which is explained at next page. The second criterion is importance, which is embedded as beta. It is the amount of information that each variable contains. If the importance of some variable is large, it is likely to be selected. In the base work, both of them are measured by mutual information criterion. The final term is hyperparameter calibrating the weights between the redundancy and importance. Now, let's see the max-cut problem to see the details of eliminating the redundancy. The max-cut problem is a graph problem to assign level on the nodes by penalizing or rewarding the coexistence on the same levels. Let's see the following graph. As you can see, we can assign 1 or 0 levels on each node and make some clusters. By assigning them, we can see that there is a connecting line between 2 clusters. The max-cut problem is a problem about maximizing the sum of the weights of the connecting lines. For instance, the values of case 1 is 1.7. The values of another case are 2.6. Therefore, the below combination is more appropriate solution than the above one. The original max-cut problem binds nodes with small weights against those with large weights. Similarly, the quantum feature selection binds features with small similarity against those with large similarity. As a result, it can eliminate the redundancy. The base work used the criterion of redundancy and importance as mutual information criterion. However, the mutual information criterion is inconsistent along hyperparameter and too general measure for the linear models. Therefore, we suggest Pearson correlation coefficient to capture the only linear relation among the features and targets. Let's see the detail. Let's see the result of experiments using our approaches. To see the performances of our suggestion, we executed 3 experiments. The first one is compare between previous works and ours. That is, we compare the correlation and mutual information criteria. The second one is compare among conventional algorithm and quantum algorithms. For the first and second experiments, we generate data following multivariate normal distribution and use first four variables as true influential variables on Y. Lastly, we also did experiments over a real data set whose number of features are 9 to 30. We used performance metric for prediction as mean squared error, AIC, and R squared, and metric for multicollinearity as conditional numbers. All of them are broadly used metric at evaluating the linear models. The first experiment is compare between correlation and mutual information criterion, aka MI. The blue line depicts the cost of all possible cases. We visualized the 10th power of 2 numbers of cases into decimal number. That is, binary numbers into decimal numbers. Because we use first 4 as true parameters, the combination of 1, 1, 1, 1, 0, 0, 0, 0, 0 becomes the optimal sort combination. The decimal number of 1, 1, 1, 1, 0, 0, 0, 0, 0 is around 1,000. So we can see that the score is best when it reaches at 1,000. The crimson line and green horizontal line depict the score of solution of each algorithm. For instance, the combination of MI got 3,000 at AIC score, and combination of correlation got almost 0 at AIC score. All of the 3 criterions are better when they are lower. The correlation measures always got better score on all of the 3 metrics than mutual information criterion. Therefore, we can say that we found better method for the linear models. Next, we performed Russell genetic algorithm, aka GA, and simulated annealing, aka SA, and quantum annealing, aka QA. As we can see, even though all of the 4 algorithms are succeeded to find combination with good R-squared, the conditional numbers of Russell, GA, and SA are not that good. Therefore, we can say that the solution of quantum annealing is good at both of the predictive power and analytic power of the models. Finally, we did the experiments over 5 different real data sets. It is better to be high for the coefficient of determination and better to be low for the conditional number. As we can see, the quantum annealer are not that good at prediction, but good at conditional numbers. Because 2 criteria are in some kind of trade-off relation, we can regard that the quantum algorithm can find a combination good for explainability by sacrificing the performances. Anyway, the results show that the quantum approaches can be used at the real data too and have some advantages. As a conclusion, we can summarize our works as finding more appropriate measures for the linear model and show the quantum variable selection can be used at the real data application. So this is the end of our research on the quantum variable selection. Based on the researching experience, we are planning to study applying the quantum algorithm into other problems. To efficiently organize the research direction, we are considering 3 steps: applications, data, and methods. The applications fields are front field where the most of the users are interested in. The biology, finance, and logistics are fields that where the problems are made. However, most of the application fields have data problem, which means that the structure of data is too complicated that they have to be handled by professionalists of the data. Because of the K.Q.C has many experts on statistics and data science, we're expecting that we can show our strengths about it. To solve the problem, we will keep research the quantum approaches in the conventional methods such as dimensional reduction, Bayesian statistics, and machine learning. Through the framework, we'll keep figuring out the potentials of the quantum computers as a pioneer of the quantum computing in Korea. Thank you for listening our presentation.
Thank you for presenting an excellent review of the research, Mr. Min.